Hey everybody, folks. Words. Hi everybody. Nice to see you all. Welcome to another lecture of 6.7350. Nice to see the few and the brave of you who are still here the day before Thanksgiving. To the rest of you, maybe share with MIT your thoughts on whether insisting on a lecture the day before Thanksgiving really serves our pedagogical and personal life goals here, but that's okay. Right, so in terms of announcements and things, it's basically the same announcement that we had every single lecture for the last roughly 3 months. You have one more assignment due and a final exam coming up. Do make sure they're marked on your calendar. I know a bunch of you guys have conflicts with the final exam, which is annoying to me because it means I have to write it a couple days early, but that's fine. I will follow up relatively soon, and we will start working with you guys to find one alternative date. I'm not doing the thing where there's like 12 different things that I have to proctor. So I'll try to find a date that works for as many people as possible, and then you guys got to make it work. Okay? Yes. Do you have a quiz this week? I believe, no. Let's just skip it. Yeah. Yeah, that's enough already. Yeah. And Mark, if you don't mind, we should start thinking about the final alternative date. So don't let me forget. Yeah. Any other questions, comments, concerns? Interesting tips to make turkey less dry? Cook a duck. Honestly, Alicia's right. Turkey's gross. Okay. So with that, let's get started. Speaking of which, I think my mom is texting. Yep, looking for where things are in the kitchen. We will deal with that in an hour. So, right, let's see. So today, we're going to continue our discussion of sort of functional style problems in numerical analysis. If you recall, our previous lecture was all about interpolation. So we were given the values of a function sampled at some distinct points, and our goal was to fill in values in between. And basically, the main message that we had is that there are clever ways to choose different bases for functions, usually in polynomial space, but not always. That essentially what we can do is choose a nice basis to write our unknown function, solve for the coefficients based on the data that we have, and we're good to go. Today's lecture, we're going to be talking about quadrature, or numerical integration problems in one dimension mostly. And we'll see that it's largely an extension of the interpolation machinery that we covered in our previous lecture. Because if you think about it, sort of the easiest way that one might come up with a strategy for integrating a function is, given some samples of the values, is to basically interpolate those values to a full function and then take the integral of that thing, right? And in fact, a lot of the quadrature rules that maybe you didn't learn that way probably can still be interpreted in that fashion. So today we'll talk about some of the clever tricks. Numerical quadrature is one of these problems that simultaneously is really, really hard and really, really easy. So today's lecture will probably feel fairly straightforward. I think a lot of this is actually covered in high school AP calculus in some version or another. I'm already losing you, Jenna. And but we'll see that there's actually some clever tricks along the way, some pretty important and interesting kind of numerical considerations along this path. And moreover, we'll see that there's some really, there's a mouse. Ugh, gross. I'm so sorry. Yikes. It's like somewhere over here. What? Well, that's not distracting at all. Oh boy. We're just gonna look, Madeline and I are gonna have a conversation about quadrature. Great. Definitely what I want to be doing today. We're going to see that depending on how we interpret these quadrature rules, some of them either feel really reasonable and then end up being kind of strange looking in a different form, or vice versa, which is a little bit surprising. Like, for instance, we'll talk about piecewise quadrature, which is exactly what it sounds like taking a one-dimensional integral, dividing it into little intervals, and then integrating in each little piece one by one. And we'll see that quadrature rules that feel like they should be more accurate, like using parabolas instead of straight lines or whatever, when you look at the actual quadrature rule just as an infinite sum, actually starts to look really strange. And so this is one of these areas that I think is a little more surprising than one might guess at first blush, but also isn't terribly complicated. So as always, we'll start a little bit with the statement of the problem and some of the applications that benefit from numerical quadrature. Oh my God, is it squeaking now? I'm gonna hope that's someone's show too. Wow, what a day. If somebody wouldn't mind sending a quick note to facilities, if you have a laptop, that would be much appreciated. I guess, this is the price we pay for having this beautiful view of the river. Wow, that's distracting. We'll start with some distractions. We'll start with some applications of Quadrature, and then talk about the basic numerical algorithms. We'll continue our discussion next week. So, to state our problem pretty clearly, in this case, it's pretty straightforward. In our last lecture, our goal was to basically interpolate some discrete values of a function to basically find some f of x that fills in the values in between the x's where we have data. Today, we're going to try and find integrals, and then probably in our next lecture, we'll talk about derivatives. These are really classic numerical problems. I'm guessing many of you have actually probably coded some rule for these things, whether you were conscious of it or not. And it's still important to kind of think of them from the perspective of the algorithms considerations that we have in this course, like error bound, stability, and so on, which maybe we've kind of intuited but haven't thought about carefully. Okay, so that's our goal today. Next time. Right, so in terms of motivation for computing integrals, I mean, all of you have taken, I hope, a calculus class of some sort, so hopefully it's not terribly surprising that people want to compute integrals numerically. But the reality is there's a lot of applications where these numerical precision or numerical routines show up in practice. And in fact, many of them range from statistics to graphics and so on. So I'll briefly mention a few. Probably the simplest one and the most obvious place is the Jesus Christ. Sorry, I really wish it didn't make. I didn't know these things made noise. Well, I mean, like that loud? I don't know. They're little guys. This is very distracting. That's a new one. My 15 years of teaching. Oh yeah, I'm sure it looks horrifying to our YouTube audience. Right, so a lot of important functions actually are defined in terms of integrals. In fact, I mean, there are functions that we use and manipulate in this course that we actually haven't really actually given you numerical routines for computing. So probably the most obvious one is e to the x. I mean, at the end of the day, you have chips in your computer for adding, subtracting, multiplying, and dividing. Probably not different chips. But you don't have an e to the x card typically in your computer. And so even some of the basic numerical functions are written in terms of routines like quadrature. So for example, if we have dx dt is equal to x as an ordinary differential equation, which is related to quadrature, we'll cover that soon, then one thing that you might know is that x of t is equal to, I guess, a constant times e to the t. Hopefully I did that right. I did. So in some sense, if we have a numerical method for solving ordinary differential equations, which is basically just integration, we'll see, then we also, as a byproduct, get a whole class of numerical methods for evaluating e to the x, which is important. There are other functions in mathematics that actually are just defined as integrals. So probably the most famous one is the one on the screen here. This thing is called ERF. Anybody know what ERF stands for? I'm guessing our resident Bayesian does. Or what was that? Error function, that's right. This thing is basically integral of a Gaussian or a bell curve. It shows up a lot in statistics and numerical methods. And in fact, these kinds of integrals are really important for not only kind of static problems in evaluating different functions, but also, for example, randomized algorithms. So for example, something that sadly we can't cover in this course, if it were 2 semesters, we could, are kind of randomized numerical algorithms. For those of you looking for extra credit, there's a whole new set of chapters for the textbook that I've drafted that cover this kind of stuff that I need somebody to read. As you've seen, I'm already pretty prone to typos. A very typical thing that we might want to do in applications is sample from some probability distribution, p of x. So for example, let's say that we have a Gaussian of some sort, like a normal distribution. And usually we think of probability distributions as having a density p of x, right? So for example, if you integrate p of x over all x, you get 1. This is like the probability that a sample ends up at some given point. So a very typical assumption is, which by the way is one that you should question, like if we had this class for longer, we would cover algorithms for this, is that your computer can probably sample random values from the unit interval uniformly. like whoa, I wrote something that looks like math, but it totally isn't. If you can sample random variables like x from maybe the uniform distribution on the interval 0, 1. Your instructor is a little bit distracted. Where essentially what this is doing is randomly drawing a number between 0 and 1 with uniform probability, right? So for example, a stupid algorithm for this is you randomly generate an integer between minus int min and int max, and then you scale that range to be between 0 and 1, and it's a pretty good uniform sampler. Turns out slightly biased, by the way. That's a interesting thing to think about. So unfortunately, we don't have pieces of code to sample from just like every possible probability distribution that you might cook up in real life, but we have all kinds of randomized algorithms out there that probably many of you have encountered that require sampling from complicated probability distributions. And this is probably the first application of numerical quadrature that comes up. By the way, the algorithm here is called inverse transform sampling. I really struggled to write like a little derivation / proof of this in the book. It's in the chapter that you guys read because it almost feels tautological. You have to be very careful how you write these things down. And especially in this class, since we don't really assume probability, like doing it with like vibey notation that's still like correct behind the scenes is kind of an interesting needle to thread. So I'll be curious if you guys have feedback. In any event, given a probability distribution like P of x here, very typical object to define is a function, maybe big F of t, which we will define to be the integral from minus infinity to t of p t dt. Does anybody know what this thing is called? Just a little bit of probability for the day. Yeah, the cumulative distribution function, right? So this is kind of like how much probability mass is to the left of t as a function of t. Obviously, as t goes to infinity, this number goes to, thank you, 1. Okay. So here's kind of a fun thing that we can do. Let's say that I have a random variable x, which I draw from the uniform distribution on 0, 1, and I have some arbitrary distribution function that I just have access to by value. A very typical situation. Then something that I can do is I can define a new random variable, which I write as f inverse of x. Notice that to evaluate this function, I need two things. I need both root finding and quadrature. Right? Because big F is an integral, which maybe we don't have access to, and I actually want the inverse of this thing as a function, which if you think about it is a root finding problem. Now, if we think of y as a random variable, right? Like I randomly draw a number between 0 and 1, and I put it through f inverse as a function, right? Then I get some new random variable along the whole real line. Does anybody know how this y is distributed? Like where are y's most likely? I'm sure some of you guys do. This is a very well-known algorithm. Well, it turns out, as a random variable, y is distributed by the function p. And so this is actually an algorithm for sampling from a probability distribution that's sort of predicated on being able to compute integrals. Let's see if we can write at least a sketch of a proof for y. By the way, this only works in one dimension. In higher dimension, you have to think about like how to extend this algorithm. And the short answer is you probably shouldn't. But in any event, let's say that I choose some number z, and I look at the following. I guess I'll write probability of y being less than or equal to some z, right? So if we can show that, notice that this is basically the cumulative distribution function of y, right? This is CDF, I guess, as a function of z of the variable y. I'm inventing probability notation as I go along. I had a 6th grade teacher that cried during our probability lesson, and I kind of blamed them for my lack of skill in this area. I'm sure we were terrible, annoying elementary school kids at the time. Okay, so what is y? Well, by definition, this is the same as the probability that f inverse of x is less or equal to z, where x is drawn from that uniform distribution defined above. Make sense? Now here's a nice thing that we can do only because probability distributions like p are positive, which means that their integrals are increasing functions. By the way, for now, maybe just for ease of math, we'll assume that p is strictly positive, so we don't have to worry about like what happens when it flattens out. That turns out to be okay. You just have to define f inverse carefully. Then one thing that you can check is that the inverse of an increasing function is a unique thing, right? Because it never doubles back down, right? So in particular, because of this, this is exactly the same as the probability that x is less than or equal to f of z, like that. Does that make sense? You can only do that because f is an increasing function. Okay. Well, if you think about it, this is exactly just f of z, because x is a uniform variable. So what did we show? We showed that the cumulative distribution function of our random variable y is exactly f, which means that y is distributed like p, kind of just by differentiating both sides. So basically this little proof justifies this algorithm, and really is one of the principal kind of applications behind the scenes where people think about numerical quadrature, because, okay, so Gaussians, it turns out there's all kinds of numerical methods specifically to sample from Gaussians, but like, if you're out there modeling some complicated distribution over the real numbers, then you just need some way to sample from it to do your Monte Carlo algorithms, and this is a very straightforward formula that works for basically any p. Cool? So that's a nice application of quadrature. By the way, if you like this kind of stuff and you want to learn how to, like, one question that I had to answer when I was writing the probability chapters of the book that you guys don't have access to, if you remind me, I can put them in the Slack or whatever it is that we use, Canvas. They're a little messy. Is like, what do people actually do to sample from Gaussian specifically? Because those are really important distributions. It turns out there's like a whole class of methods that do it. So this is one of them. I think in reality, there are like clever algorithms for evaluating this error function that are a little better than just generic numerical quadrature. Another thing people do, just if you want to read about this stuff, because I know we have some statisticians in the class, is if you look at the Box-Muller transform, this is I think there's an umlaut there. It's definitely not the same Muller as the, well, I guess he's not going to prison now? I'm confused. Anyway, different Muller, mathematician, which does a really interesting thing. It takes uniform random samples in the unit square, so it takes two random variables and maps them to two Gaussians, but like in a way that like doesn't make sense in one dimension. Like it's kind of a clever thing, and you get two random variables that are independent for free, which is kind of surprising. So anyway, hopefully I've convinced you guys that quadrature is important at least for one-dimensional probability. We'll come back to the high-dimensional case in a minute. Every time someone enters in that door, I'm nervous now. It's not you, Leticia. There's an event here earlier, and so that's particularly the technique that we've defined today, which is inverse transform sampling. To give you an example of numerical quadrature in a completely different field, the world of computer graphics, arguably, is basically just one giant integral computer. So in particular, there's this really fundamental equation, which strangely doesn't usually get covered in graphics class till the very end, because I think it's, I don't know, it has an integral in it. That's kind of scary. It's something called the rendering equation, which in some sense is like, we don't usually think of like rendering software, like video games, ray tracers, whatever, as solving an equation, but they totally are. Out of curiosity, has anybody encountered this? I know we have some graphics students here. Yeah, so it's called an integral equation, which is sort of like the souped up version of partial differential equation for things that aren't local. I'm going to rush through this a bit because we were distracted at the beginning of class. Although our friend seems to have left the room, which is good. Okay, so this is, by the way, I believe the first person to propose this, the very famous computer graphics researcher from the Middle Ages by the name of Kajiya. I should be respectful. I think he's alive. Right. So in particular, I'll co-opt this mark on the board. We'll define a function I, which is going to be, I always confuse the arguments. We'll say I of x comma y is like the intensity of light. So like I'm drawing a 3D scene and I'm trying to figure out the colors basically, and like the brightness, all that good stuff. And I'm going to say that it's the intensity of light going from y to x. Almost certainly in about 20 seconds, I'm going to swap x and y, so just get excited for that. And the rendering equation, basically, in some sense it's a model, but it's a pretty darn good model. I think like in some sense, if we somehow had a machine that could actually solve this equation, it would be better than the rendering tools that we have today, modulo some weird effects like media where light takes curved paths or something like that. But basically, it looks like the following. We have a g of x, y times, I'm going to write it first, and then I'll explain all the terms. For some reason, I think I forgot to put it in the slides, so I'm just going to write it. Rho. So for now, well, no, this is fine. Easy. Okay. So what is this equation saying? It's saying, like, basically, think about what happens when I look at light moving around in a room, like this classroom here. Now, typically, when we think about rendering, oftentimes we jump straight to the algorithm, but we don't think about the physics involved, right? So like a very typical thing to do when you're drawing a scene might be to just like go object by object by object in the room and just paint it. But that's not really how light works, right? So in particular, like there's light coming off the ceiling, it's bouncing off of my shiny bald guy forehead, it's bouncing onto these chairs, and then back onto me, and then back onto the chair, and then into my eye, right? Like there's all kinds of crazy things happening in the room. For the most part, that's negligible, and that's why rendering tools work so well. But there are cases when it's not. So for example, if I shine a really bright light on the wall, I'll see it on the floor, right? Even though like the wall isn't probably a material we would think of as reflective, right? Or even worse, like if I have a magnifying glass, it will take light and move it along some nonlinear paths that probably I couldn't get by like rendering from the perspective of the viewer, right? And so for those kinds of things, we need tools for a task in computer graphics called global illumination. Exactly what it sounds like, illumination. Sorry, I kind of ran out of space. And global illumination says, instead, I need to account for all the bounces of light going every which way, right? And so that's what the rendering equation is for. And it has a bunch of terms in it, which in some sense are determined by the engineer, the person drawing the scene. So for example, d of xy is a geometry term, which is basically just attenuating the light that goes between x and y. So think about like, you know, if I'm rendering this room and the lighting is coming from the window in the back of the room, then the fact that this camera is here means that some of the light gets blocked, right? So if x and y along that line have the camera in between them, then g should be what? 0, right? It should just zero out the light. That's the transmission term there. Now here we have an emission term, right? So like for instance, I guess at y, if there's a light bulb, then there's like a positive amount of light coming in without a real source. Of course, this is non-physical. Like really, you should be modeling, I don't know, like the electrical things happening inside the light bulb, but this is kind of where we stop. We have rho, which is like scattering. And then notice we have another I on the right-hand side, which is what's making this thing an equation we have to solve, right? So think about what's going on. Like I draw, for example, a little, so here S is like the surfaces in your scene, right? And so when I talk about the light coming in, what I have to do is take a giant integral over all the surfaces in my scene and look at all the light bouncing off of each of those surfaces and then hitting me, right? So that's basically what this complicated equation is saying, is that the light that hits me is basically the sum, I see, of light that came directly from a light source and then light that bounced off something else, typically with some attenuation term in front of it like rho. Now, even if I've probably messed up all kinds of constants here, I think you guys can basically see why this thing is a weird giant equation. And moreover, notice that there's an integral heading here. And so you can think of rendering tools as basically approximations to that integral, right? So for example, the basic rasterization tools that you might have learned in computer graphics software that just draw one triangle at a time, probably just zero out this term altogether, and then now you can just directly, draw your scene. Or there's algorithms out there like photon mapping, radiosity, and so on, which try to model these bounces. A very typical thing to do, like if you think about it, well, I could take this expression and I could plug it in there, and then I get a double integral. And then like a very typical thing to do is just stop after 2. That's a good approximation. So in other words, to say like light that bounces more than twice probably had to come from a direct light source because surfaces tend to absorb a lot of energy. In that case, you end up with an algorithm that's kind of similar to path tracing, right? So basically a lot of graphics tools can be understood in terms of like basically quadrature for approximating this integral. One annoying thing is that, of course, this integral is often very high dimensional and large, right? You've got lots of surfaces in your space. Jonah.
You answered my question. It was the what, like, how do we stop bouncing?
Yeah, how do you stop bouncing is a good question. It's one that I have to answer every morning. And you've made a face at me. I just whatever. In fact, some algorithms don't. I mean, so the popular algorithms today basically fall into two categories. There's like ray tracing style algorithms, and rasterization basically has to do with whether you trace lights of whatever rays of light bouncing around your scene, or whether you just draw one object at a time. There's a third class that used to be very popular in the 80s, but they come up every once in a while, called radiosity. Has anybody ever encountered radiosity algorithms before? They're super cool. In fact, really, I should bug your TA with this stuff because I wonder if some of the stuff she's doing are irrelevant. There's a whole set of algorithms out there that try to solve integral equations directly. Like many of you have probably encountered the finite element method. There's a version of that that works for these kinds of things. And what radiosity does, which is totally wild, is they just take the entire 3D scene, divide it up into blocks, like tetrahedralize it or something like that, and then just write this thing as a big linear system of equations and try to solve it. And that was, I think, among the first algorithms for doing global illumination, is to just write basically a big matrix. Do you guys see that this is linear in the unknown? There's I on both sides. So you can do that kind of thing. Which leads to a giant, dense matrix that's hard to work with. So I think these algorithms are not super popular in practice, but it is kind of cool that people, even like decades ago, were able to do this and get some version of global illumination. If I recall, if you look at these old figures, they tend to look kind of chunky, which makes sense because like they have to take your 3D scene and divide it up into little elements, and that gets expensive very fast. I actually don't know if people have thought about it very carefully in light of like modern algorithms for tetrahedral remeshing, which is kind of what you need for this kind of thing. In any event, integrals show up everywhere in our everyday life. I mean, to give you a grab bag of other ones, I don't think we'll go into details. Those of you who are into signal processing have no doubt encountered integrals all over the place. So for example, if you want to blur out an image, a very typical way to do that is to define every output pixel as some integral over the image of the input pixels. For example, here's a Gaussian convolution. Or to go back to probability, probably the most annoying and popular source of integrals today comes basically from Bayes' rule, which is all about sort of understanding the probability of an event x in terms of y, given the probability of an event y in terms of x. So for example, maybe I develop a big probabilistic model, like, now of course I'm like struggling to think of a goofy example of a probabilistic model. Like I want to know a random variable like, will I eat breakfast today? And that variable is dependent on the number of hours that I slept and the amount of noise outside of my bedroom. So for example, this morning my parents were awake at 6 a.m. cleaning around the kitchen. And each of those things is probably dependent on other random variables, like my parents' sleep is dependent on the flight time that they had the day before, or whatever. So I developed this big graphical model, this big chain of random variables that all depend on each other. And then typically at the very top of that chain, I put some prior. Like I think, like the distribution of flight times is roughly Gaussian or something like that. Now I observe something, like did I wake up on time this morning? The answer is, actually I woke up early. And now I want to propagate back to all those other random variables, that likelihood information, right? I have to update my posterior. In order to do that, I want to apply some version of Bayes' rule. And sadly for us, there's this pesky denominator underneath. And in fact, I think if you guys take a probability class, there's like all the time you see all these expressions that look like 1 over z, f of z, where f is like something that's basically the density of a function up to some constant. But sadly, a lot of algorithms actually need probability values. They don't need things that are proportional to probability. And so that leads to having to cope with that constant, which is a giant quadrature problem. Yeah. Now the difference is that in typical applications of probability, these are very high dimensional, which means that most of the algorithms we'll cover today are no longer relevant. But just so you're aware. Cool. Incidentally, these days, like what's all the rage in the last couple of years in like generative modeling and so on, is that a lot of algorithms are not written in terms of probability density. So like let's call this maybe P, oh oops, that should be an X. Sorry. Call that P of X. A lot of sampling algorithms now, both in Monte Carlo and in like diffusion models, are written in terms of grad log P of X. Now, there's all kinds of probabilistic reasons why this is a useful function. Does anybody know the name of this thing up to sign? The score function, which I consider to be like the worst terminology ever. In my mind, like a score should be a number, not a vector, but whatever. From perspective of today's lecture, any idea why score function is somehow a useful object? Just purely practically speaking, never mind from probability perspective. Let's think for a second. This is our expression for p. What happens if I take grad log p? Well, okay, let's think one term at a time. So log p is going to be log of f minus log of z. But z is a constant, so what happens when I take the gradient of it? Yeah, so grad log of p is actually equal to grad log of f, meaning that like I don't need that normalization constant anymore, right? So if I can write my sampling algorithm just in terms of the score function, I'm actually cooking with gas because I don't need the hard to access weird constant number that's needed in a lot of corners of probability. Right? So in any event, like I think when you read a lot of these algorithms in this space, they talk about it as this very sort of high concept idea of why you might want the score function. And of course it has all kinds of nice interpretations, and there's differential equations and SDE, all these other things. But the reality is it's also just the object we tend to have access to, which is why these algorithms are successful. But don't tell anybody I said that. Okay, but for today, we're not going to talk about these problems because they're very high dimensional. We'll kind of mention it in our next lecture. Today, we're going to talk about one-dimensional problems, one-dimensional integration problems, and higher dimensional, but especially in one dimension, we typically call quadrature problems. I think the reason why the term quadrature comes up is just that integration is kind of an overloaded term. In particular, we also use it for integrating a differential equation, which is related, but not exactly the same task. We'll cover that 2 lectures from now, I hope, if I manage to not talk so much. So the quadrature problem is basically what's stated on the screen here. So you're given a sampling of values of a function, different points, xi, and then your goal is to estimate the integral on some region. If you dig into this problem, you'll see there's actually a lot of different variants of the quadrature problem. So for instance, for some quadrature tools, we might want to be able to query multiple A-B pairs. Like we don't know ahead of time which integral we want, but we have like a fixed set of samples. It also could be that we have access to our function f as a function, right? Meaning that like there's a piece of code where I can put it in x and it gives me back an f of x. Relative to like there are other applications, for example, maybe in statistics where like, no, I just have a list of x comma f of x pairs and I want to get the best possible approximation. Do you see how these are like a little different? It's kind of like in machine learning, like the difference between active learning and passive learning, supervised learning. You know, that like one of these you can strategically choose x's that you think are going to make your integral better, and the other like I just have a list of data points ahead of time and like I can't go out and collect more, right? Depending on your setting, you have one or the other. Notice that the second one is one that we're actually going to return to, hopefully. I think an undervalued thing that we often don't think about in the undergrad version of numerical quadrature, which is not this course, is that you can strategically choose your x's. They don't have to be a grid, right? And that's sort of a neglected fact. I think oftentimes the table stakes for a lecture on numerical quadrature is that you have x's on this evenly spaced object. But in the setting where you can query f anywhere, there's a lot of different things you could do. It turns out you could just initially distribute your x's in some fashion, like maybe the boundary of the integral AB matters more than the inside. I don't think that's the case, but it could be. Or maybe you do it adaptively, like you start collecting a few samples, you see where you think the cool action is happening in your integral, and then you oversample in those regions. Right? These are all different algorithms that you can do. Okay. Everybody with me so far? The good news, I think this is an easier topic in this class. A lot of the things at the end actually are much easier than optimization stuff. Okay. There are all kinds of different objects out there that we're going to call quadrature rules, which are basically different ways of combining these samples together. You see that basically, once you have this list of samples, what are you going to do? You're just going to munch together this list of xi's and fxi's into some formula for the integral. And they tend to be linear, right? I mean, they tend not to be terribly complicated, which makes sense because integrals are linear. So linking to our previous lecture, the biggest class of quadrature rules, for good reason, is a set of rules called interpolatory quadrature rules, exactly what it sounds like. So what do interpolatory quadrature rules do? They take any of the interpolants that we had in our previous lecture, and basically all they're doing is flip-flopping an integral and a sum, right? So in particular, let's say that we had our data point and we borrowed one of our interpolants from the previous lecture. Anybody remember any of the bases that we had for phi I? Any of the polynomial bases? Literally any? Functions, but what kind of functions for? Half functions. Half function basis is a good one. What else? Monomials. Yeah, we're not in love with monomials, but they count. No, okay, so maybe we review that lecture when you get home. Okay, but in any event, hopefully we see that if we write f as a sum, like the first term here, we can swap the integral in the sum. And now, what do we have? We have basically the AIs, which are determining our interpolant. So that came from the lecture last time. And then these integrals, but typically these are known in closed form, right? So we can say, well, really, this is just some weighted sum of the AIs. Does that make sense? And the C's here just come from integrating our basis functions. So for example, since Jonah is so in love with the monomial basis, let's say that our basis here, like phi k, yeah, so let's say that I write my interpolant f of x is equal to, oh no, the sum over k of a k x to the k, like that. Notice that like we don't like this because obtaining the AKs is kind of annoying. Do you remember this? You have to solve a particular linear system of equations. So like just acknowledgement of any sort is super helpful. Don't make me talk to the mouse. Okay. Right. So in particular, anybody remember the name of that linear system? You got the syllables right, but in reverse order. Vandermonde, or what are the fancy European ways of saying? Yeah, you solve the Vandermonde linear system of equations for the A's. And now to compute the integral of this thing, I'll give you, because I'm a nice guy, a formula, which is the integral of xk from 0 to 1, which I believe is 1 over k plus 1, the last I checked. Okay, so in this particular case, what do we know? We know that the integral from 0 to 1 of f of x, well, it's the sum over k of ak over k plus 1. Does that make sense? And so, in some sense, what do we do? Well, in general, this is some weighted sum of the coefficients. In this case, the weights are kind of interesting. They're like a decaying, like a harmonic series. And that's sort of a very typical idea of what we'll call a quadrature rule. Okay? Now, in general, in this case, remember that A's, they came from symbols of the function, right? In fact, they're linear in those if you kind of reshape that matrix. And so, in general, a quadrature rule probably takes a form where input's in some sense a function, but it's only going to evaluate it at a finite set of places. And it evaluates some expression like wi of f of xi, like that. That makes sense? So basically all of our algorithms for computing integrals are basically just different formulas of the following kind of generic form, where I evaluate my function at a few different points, and then I weight them together in different ways. Yeah? Notice that this expression is like that, but you also have to put the inverse of the Vandermonde matrix to actually write it in this form down here, which we're not going to do. But does this make sense, like with the definition of a quadrature rule? And notice that that's not just the case for interpolatory quadrature. So for instance, I think probably the first definition that all of you guys saw for an integral is the Riemann integral, which basically takes the integral from a to b, divides it into little rectangles, and then writes our integral as a sum over those rectangles. I'm rushing through this a bit because I think this is pretty intuitive. And of course, if I just halted this limit at some point and wrote it as a sum, that's a pretty good approximation. And notice, once again, it's basically some weighted sum of values of f times, in that case, like the width of the rectangle. In fact, we'll see in a minute that it does happen to be an interpolatory quadrature rule, but at least in the way that we written it here, it's not, well, not 1000% obvious. Okay, so generically, in some sense, the objects that we'll study for the rest of lecture are just formulas of this form. And it's kind of interesting that like more than one of these exists. In some sense, so for example, like if all of the x's are just uniformly spaced on an interval, there's an obvious thing you might do, which is add them all up, all the f's up, divide by n, and multiply by the width of the integral, right? I think that's sort of like the most obvious quadrature rule. But what we haven't justified is that there aren't other ones out there in the universe that do better. Yeah, and at the end of the lecture, we'll also talk about, like, it feels like, in some sense, the engineering of a quadrature rule is sort of a linear problem, like you're choosing the W's. But actually, we can also choose the X's, which makes this a nonlinear problem. And we'll see some examples of quadrature rules that can actually double their precision by strategically choosing the X's and the W's simultaneously. This is kind of cool. I love these things. They're called Gauss quadrature rules. Okay. Everybody with me so far? Now we're going to rush through a bunch of boring quadrature rules. They're in the book, and they're also things that I think you guys have done at home. But we'll give them some names because I think that's important. So in particular, I would say the most famous set of quadrature rules are called Newton-Cotes quadrature rules. I get the impression that Newton is like a bit of like an academia mean girl, so my suspicion, having never read the history of these, that Cotes had a lot to do with the actual derivation of these formulas, but like, what do I know? And basically, the Newton-Cotes quadrature rules make one additional assumption, which is just that we evenly space our xi's. That is an assumption. We didn't have to do it, but these quadrature rules make that assumption. And moreover, they're going to be derived basically directly from interpolation. So for instance, if I have 3 points, then I'm going to interpolate them as a parabola and then use the integral of that parabola as the integral for those 3 points. Does that make sense? By the way, to be clear, like if I do Newton-Cotes rule with like 10 points, then I'm going to interpolate a degree 9 polynomial, which is probably not so great. So we'll come back to how to fix that in a moment. Now, there's 2 different categories of Newton-Cotes rules, closed and open. I think this diagram pretty much shows you exactly the difference between the two, which basically involves whether I put an x on the endpoints or not. We're going to see that that doesn't actually affect the accuracy a whole lot, which makes sense because it's basically 2 out of a big set of n samples. But it is true that technically they're slightly different quadrature rules, right? Like in the closed case, you're likely to have sort of an extra 1/2 term in front of the first and the last thing in your sum. So let's go over some examples of Newton-Cotes rules. I had fun drawing these. Okay, so the simplest one is the midpoint rule. This is the world's dumbest integral, right? So I get one sample on the interval from a to b. So by symmetry, I probably stick it right in the middle of that interval. So my integral I approximate as just the value at the midpoint times the width of my integral. Yeah, everybody with me so far? I warned you this is going to be boring stuff for a while. And that's an open rule, right? Because the midpoint is neither a nor b. The simplest closed rule basically averages the values on the 2 endpoints and then multiplies by the width of the interval. It's called the trapezoid rule for obvious reasons. Notice that I've moved from constant interpolation of my data to linear. And we don't have to finish there. Like, for instance, I feel like high school calculus students are like really into the next one in the sequence, which is something called Simpson's rule, where I have 3 points. And now I find the parabola that interpolates those 3 points, and then I compute the integral of that. And I get, fun fact, I get this formula here. I don't think we need to derive it together, because at this point, well, I hope you guys can compute integrals. Any questions so far? And you all have in your mind like how you would go about deriving this formula? Cool. All right. Now, beyond degree 2, I think it's pretty uncommon to use Newton-Cotes rules. I mean, in principle, you could do like all kinds of crazy polynomial interpolants. But as we saw in our previous lecture, you start to get these crazy artifacts that happen. They tend to be quite unstable. You might notice already that these formulas start to look a little strange. Like, why should it be that in my integral, I have 4x the weight of the middle point relative to the 2 endpoints? But if you think about it, like I have 3 pieces of data that are sort of equally reliable, and yet I'm amplifying the role of the guy in the middle. And I think that's the thing to kind of think about with these quadrature rules, that like somehow we have 2 brains. On the one hand, this feels more accurate because we have parabolas instead of straight lines. On the other hand, the weighting is super strange. And it's not clear how to rectify those 2 observations. And we'll see that like a little bit of Taylor series can help us out. So typically, rather than doing higher and higher degree polynomials, what we'll end up doing is deriving things called composite rules, which is exactly what they sound like. So now, for instance, if I have composite midpoint, then I take the region from A to B, I divide it up into a bunch of intervals, and I do the midpoint rule on each of the subintervals. And each of these things is pretty straightforward to derive. For instance, there's composite midpoint, composite trapezoid. Notice that these are starting to look similar. Right? Both of midpoint and trapezoid are basically just the average value times the width of your interval up to like terms that basically decay and go to 0 on the two ends of the boundary. Composite Simpson, notice it needs an odd number of samples for obvious reasons. Now kind of takes every 3 and makes a little parabola. One thing that's worth noting, notice in this picture, there's a derivative discontinuity. And like this is actually a pretty bad interpolant, but that kind of doesn't matter from perspective of the integration rule. This thing has a really strange form. So again, like essentially what I'm trying to emphasize to you guys is that like rules that feel totally reasonable and maybe like, oh, well, of course I can increase the accuracy of my integrator, from perspective of the second formula, to me look a lot stranger, right? Like I think if you were to guess how to compute an integral of a function given evenly spaced samples, you'd just compute the average, like some version of that, and then multiply by the width of your interval. But notice that's not what composite Simpson does. On every other sample, it puts a weight of 4, and every other sample, it puts a weight of 2. And so I think a totally reasonable question is like, is this a good thing to do? Like, Taylor series might say yes. Your horoscope might say no. So let's dig into that a little bit. In particular, we need to figure out which of the quadrature rules is the best one. So let's do a little bit of math. And in particular, we're going to derive kind of a surprising result, which is that, for example, the midpoint of the trapezoid rule, they look like they should differ by 1 order of magnitude as delta x goes to 0 in accuracy, but that turns out not to be the case. And it has to do with the fact, specifically, that in the midpoint rule, we put our sample right at the middle of the interval, and nice symmetric things happen. Okay. You ready for some boring math? Cool. All right, so in particular, here's what we're going to do. We're going to write the Taylor series for our function about the center point of our interval. So we have f of x is equal to the f of the center point plus, and now I can never remember how many terms I actually need in this Taylor series, so we'll write a bunch just so we have it around, plus 1/2 f double prime of c times x minus c squared plus 1/6 f3 of c x minus c cubed. And I believe in my math, yeah, see the unfortunate thing, yeah, we need one more term. This is annoying, sorry. Plus 1/24, which I believe is like some number factorial. The fourth derivative of f, c, x minus c to the fourth, plus finally, big O of x minus c to the fifth. The good news is we're going to make very accurate integrators. That's why we need all these terms. Okay? Hopefully I wrote my Taylor series right. You guys are very agreeable. I mean, we make mistakes all the time. Okay, so one thing we can do is take this expression and just integrate both sides from a to b, right? And in particular, a really nice thing happens. What is the integral of this second term from a to b? Remember that c is the midpoint. You're all whispering the right answer. Somebody speak up. 0. Do you see that? Because this is a symmetric function about c. It's positive on one side and negative on the other. Similarly, what is the integral of this term about from a to b? 0. Right? And so this is why we need so many terms in our Taylor series, that actually when we integrate it about the midpoint, notice if we didn't choose the midpoint, this wouldn't work. Then a lot of things disappear by symmetry. In particular, I find that the integral from a to b of f of x dx, well, it's b minus a times f of c, right? That's the integral of the first guy. And now we skip the second. We have the third one, which is going to be, I think, 1 over, I'm bad at thinking through constants in front of other humans, so I wrote it down in my notes. B minus a cubed, right, because we integrate the square. Plus, fun trivia fact, 1 over 1920, the constants don't matter here. Fourth derivative of f, c, b minus a to the fifth, plus dot, dot, dot. Okay? So all I did was integrate the previous guy, and this is just a polynomial. I think we can all do that at home. Okay. Ah, what is the integral of something squared? It's something cubed. Yeah, so basically everything went up 1 degree. Yeah, good question. Okay, So notice, by accident, we just derived the accuracy of the midpoint rule. Do you see that? In particular, that's midpoint, right? So if I shuffled all the other terms to the other side, right? So basically I have this guy is equal to the integral plus minus all these other terms. I derived the first result on the screen, which is that the midpoint rule is third order accurate. Okay? Oh my goodness. Ugh. All right, so that's the midpoint rule. Now, unfortunately for us, we have to do even more ugly math to figure out the trapezoid rule. We're not going to do Simpson because I don't want to. Okay. In particular, let's evaluate f of a and f of b. So f of a, let's see, how many terms am I actually going to need? The quadratic guy. Yeah, that's fine. I believe I can get away with a quadratic. Yeah, okay. So it's going to be f of c plus f prime of c b minus a plus 1/2 f double prime of c b minus a squared plus dot, dot, dot. And similarly, I can write f of b is equal to f of c. I feel like this is one of these areas of math where like the amount of writing is like not worth the excitingness of the result. But we should derive this particular one. Wait, f prime of c plus b minus c, sorry. Plus 1/2 f double prime of c b minus c squared. Okay, so all I did was plug a and b in for x in this expression here. Did I manage to get it right? F of a. Let's see. So I plugged in x. What did I do? Wait, give me a second. Yes, it should be a minus c. I'm sorry. Yeah, sorry. You're absolutely right. Okay, there we go. Thank you. And now we're good. Thank you, Alicia. Okay. So notice, by the way, a lot of proofs in this domain look very kind of ad hoc, and this is no exception. What is the trapezoid rule? Well, if you think about it, the trapezoid rule, just by definition, is equal to b minus a times f of b plus f of a divided by 2, right? That's what we already wrote down. And now we have expressions for these two guys, and we can plug them in and do some ugly stuff. Okay. And essentially, what we're going to find is as follows. I'm like debating, do I just skip a bunch of steps and write the final result, or do I do a bunch of arithmetic? All right, well, let's think it through for a minute. So we have b minus a times the average of those two functions above, yeah? So let's think about the first term. Well, the average of f of c and f of c is f of c, yeah? So the first term is going to be b minus a times f of c, like that, okay? Now the second term, now things become a little bit more annoying. The 1/2 becomes a 1/4 because we're doing the average. We have an f double prime of c, and now we're going to have a minus c squared plus b minus c squared. Notice that that's just combining those two things above. Yep. And actually, I think that's, I know, thankfully. Cool. All right, and by the way, here is where I am going to spare you a little bit of arithmetic. Remember that c is equal to the average of a and b. So I can plug that into this quadratic expression here because I'm a sucker for pain. And what we will get when the smoke clears, if you trust me, it's okay if you don't. Notice I have, oh, oops, and there should be a b minus a factor. I'm sorry. Just like this guy. I just forgot to copy it. Okay. This is all in the book. I mean, you guys see some of you frantically writing. It's okay to just, I think this one's pretty easy to follow. Okay, so now, if I just expand this whole thing and then simplify, because again, I have low value on my time, what I'm gonna get is that this is equal to 1/8 f double prime of c times b minus a cubed. That's not so bad. This is not obvious. It just requires a bunch of arithmetic. There's nothing exciting here. It's just a bunch of stuff. Okay? Now, here's something super interesting and weird. What is the first term? It's the value of the midpoint times the width of the interval. This is exactly the midpoint integrator. So notice what we accidentally derived. We showed that trapezoid is equal to midpoint plus some term, which is cubic in b minus a. Yeah? So notice that we accidentally derived the second result on the screen. Because we already know that the midpoint integrator is cubic. And what did we show? We showed that the difference between the midpoint and the trapezoid integral is itself cubic, meaning a byproduct of that is that trapezoid is also a cubic integrator. Okay? Now, if we actually plug in the math that we did before, we will find, so basically, one thing that you can do is say, okay, well, we know that midpoint is equal to the integral of f minus these Taylor series that are written above. Does that make sense what I'm going to do here? If I plug those in and continue to do arithmetic, what I'm going to find is actually kind of a surprising result. This is equal to the integral from a to b of f of x dx, that's like that term up there, plus, after you do a little bit of simplification, f double prime of c times 1/12 b minus a cubed plus order delta x to the fifth. The fifth term doesn't really matter. It's a cubically accurate integral because the rest of it is even smaller, right? But the thing that I want to highlight is the constant. Okay? So in particular, we end up with a constant of 1/12 here. And let's take a look at our midpoint integrator. And because I think it's like a really surprising result, which is the following. A coefficient of 1/24. Let's think about this. This is like super strange. So first of all, which of these two integrators, midpoint or trapezoid, in some sense took more time algorithmically? Like trapezoid, right? Because I had to evaluate my function twice, and midpoint only has to evaluate it once. However, and moreover, trapezoid rule came from linear interpolation, whereas midpoint came from constant, which might indicate to you that one would be more accurate than the other. Now, asymptotically, we showed they're the same. And in fact, if we dig into our constant factors, right, the constant factor in the cubic term for midpoint iteration, for midpoint quadrature is like 1/24. The constant term in the cubic term for trapezoid integration is 1/12. So do you guys see this surprising result? If I give you the option of these two integrators, which one should I probably use? Midpoint. This is totally counterintuitive. And in fact, one thing you can see if you extrapolate to the higher order polynomial is exactly the same kind of pattern. So every two of them end up with the same order of accuracy, and the constant factors, I believe, always flip. Yes, Jonah?
So why consider all these other rules of midpoint? Like, are there cases based on the structure of our data?
It's a good question. Well, if I have a linear function, which of these integrators will do better? Well, actually, you agreed too quickly. It turns out that like either one will do okay, if you think about it, because midpoint actually will do the same because of the symmetry of a line. But for example, if I have a quadratic function, then clearly, like if I use Simpsons, I'll get an exact integral. If I do midpoint, then I won't, right? We'll see that there's even more detailed considerations later. But all this is to say, you probably wouldn't use trapezoid rule for many of your integrator problems, but I don't think that's obvious a priori. I think like had I stopped one slide earlier, you guys probably would have agreed that actually trapezoid is a more accurate one. So these are the kinds of subtle things that come up in this area that you really have to measure quite carefully. Now, of course, all of this is just a single integral that we've approximated with either 2 or 1 value. The reality is we want to do these composite rules. And now one thing you'll notice if you look at the numbers here is that they decrease by 1 order of accuracy. Which is maybe a little bit surprising, but this is actually more of a convention in the field than anything deep mathematically. And that's because typically the thing that we want to integrate is like the integral from a to b of some term, right? It isn't the integral from a to a plus delta x of some function, right? So like if I took delta x to 0, right, then I'm getting a different integral every time I do that. That's like kind of unfair. Do you see that? And so like if I want to always integrate from a to b, and I divide it into pieces, which I've managed to do unevenly, each of which is of width delta x, how many pieces do I need, roughly? Like, how many of these intervals are there? Like, number of intervals. Yeah, it's like roughly b minus a over delta x up to rounding and all that other stuff. Now, what does that mean? That means that, like, do I apply the midpoint rule once? No, I apply it per interval, each of which has cubic error, right? So essentially, I've incurred a sum over a term that roughly looks like 1 over delta x, which explains the loss of accuracy in some sense as I move to these composite rules. That's not to say that I should always use midpoint without composite over midpoint with composite. It's just that the delta x is sort of interpreted differently, right? Like here, we're thinking of it as like the width of our interval is fixed and the number of samples is increasing, whereas in our previous derivation, the width of the interval is kind of flexing with delta x. Does that distinction make sense? I think this is often just like a point of confusion. Okay, so these are all kinds of different quadrature rules, and these are the really basic ones, and all this is to illustrate that even in one dimension, these problems are already kind of subtle. Now, luckily for us, we still have a little bit of time left in today's lecture, so I thought I'd tell you about some more exotic quadrature rules that you're less likely to have seen in the past. In particular, I think there's one that I think is neat. So we've got about 20 minutes. We'll cover it today. And that is a class of rules called Gaussian quadrature rules. And they actually come from an even bigger class, which is a great way to write exam problems, and a great way to generate really hard algebraic geometry problems. I promise those two will not be the same. Which derives integrators or quadrature rules using yet another set of axioms. So far, what have we done? Like we've, for instance, done an interpolatory rule where like we just interpolate to a function, take the integral of the interpolant, and then derive. A different thing we could do is just write a list of functions whose integrals we know and say, I want a quadrature rule that gets these 10 functions exactly right. Right? Like I have like 10 functions whose integral I want, and like what I want is 0 error on those 10 functions, and then everything else be it as it may. Right? And that leads to a strategy for quadrature, which is so much fun. This is so cool. And it's like one of these things that feels obvious, and then you dig into it mathematically, and you're like, oh God, this is terrifying. Called the method of undetermined coefficients. And now I'm guessing many of you have seen the midpoint rule before. Has any of you guys seen this little thing, this nugget? This is a fun trick. Okay, so here's the basic idea. Let's say that I write my quadrature rule Q of f as the sum wk f of xk, like that. And I'm trying to derive a quadrature rule. So like at the end of the day, I'm trying to derive the w's and the x's, right? And so far, how have we done it? We've like written an integral formula and then just kind of like plugged it into this thing. A different thing is to start with this formula and then kind of regress the right coefficients. And that's what the method of underdetermined, or I guess undetermined coefficients does. Is we're going to basically make Q work perfectly for a set of functions fi. So what do I mean by that? Essentially, now I'm going to write down an algebra problem. So let's say that in version 1.0 of my algorithm, I fix the xi's. So they're just given. So maybe they're just evenly spaced on an interval. Okay? And now I have some set of functions fi. What I can do is just set these two things equal to one another and then solve for the w's. Okay? So let's do an example. So example, notice that the integral from a to b of x to the ith power, we're going to put an I there because we've got a lot of indices happening here. The i's and the k's don't have to agree. What is this thing? This is b to the I plus 1 minus a to the I plus 1 divided by I plus 1. Yeah? So for example, let's say that I applied the method of undetermined coefficients, and I said, I want a quadrature rule where somebody has given me a list of the x's, so like I don't have to worry about that. And moreover, I want it to work perfectly for the set of polynomials up to degree, I think, n minus 1, where n is the number of terms in the sum. How could I do that? Well, for example, I could write the I equals 0 case, right, which means it's basically the function x to the 0, right? So what is the integral of x to the 0? It's just b minus a. And this is equal to, in our quadrature rule, right, the function x to the 0 is just 1, so this f goes away, and it becomes w1 plus wn, like that. Okay? Similarly, I could do I equals 1. I'm going to get b squared minus a squared over 2 is equal to w1 x1 plus wn xn. Right? Because remember that the x's here is just some list of points somebody has given me, and I plug into my quadrature rule. Remember that this is f of x equals x in this case. And now I get some expression that my quadrature rule has to satisfy if I wanted to integrate, I guess, linear functions exactly. Does everybody understand what this expression is saying? And I can do this a bunch of times all the way to I equals n minus 1, in which case, yeah, I'll get b to the n minus a to the n divided by n is equal to w1 x1 to the n minus 1. Sorry, it's easy to have off by 1 errors. This is why I keep glancing at my notes. wn xn to the n minus 1. So again, remember the x's are given to us. It's like a list of numbers. And what I don't know is the w's. And I'm deriving an integration rule where at least for the set of polynomials up to degree n minus 1, my integration rule is perfect. Do you see that? Notice that this is a linear system of equations. Right? At the end of the day, it looks a little something like this. You guys can probably guess what the matrix is that's going to come out of this. Okay, so I can isolate the w's, and I'll get a problem that looks like 1 x1 1 to the n minus 1, 1 x2 to the n minus 1, all the way to 1 xn to the n minus 1 times w1 to wn, I'm running out of chalk, is equal to b minus a. Let me switch chalk so that it's legible again. And then we have 1/2 b squared minus a squared to 1 over n, b to the n minus a to the n. Does everybody agree that this is just a reshaping of what I wrote above? This is the linear system of equations. I can just solve it for the w's, and then I have an integrator that works perfectly for polynomials up to degree n, because I derived it that way. Does that make sense to everybody? By the way, do we recognize this matrix? The Vandermonde matrix, wrong. The transpose of the Vandermonde matrix, but close, yeah. Basically the same. But in any event, this is actually a totally reasonable strategy for deriving quadrature rules. Notice that this is not the same as like midpoint integration or anything else. In fact, there are these weird exponents here that make it so that like it's hard to write it in closed form. But now, what's I think is super clever and like just didn't occur to me at all until I was reading about this stuff. Now, this quadrature rule works for polynomials of up to degree n minus 1. Do you guys see that? By the way, that should be yeah, that's an I. I claim we can make a quadrature rule that works up to degree 2n minus 1. Any ideas how we're going to do that? think this is so cool. It's like such a clever idea. This Gauss guy, clever. Let's go back. Like this version, like this linear algebra version is very tidy. And basically we use it to solve for the W's. But notice that I stuck something past you guys. Which is if I'm inventing the quadrature rule, so it's like street rules, I get to like choose what the name of the game any way that I want. And in particular, I can say there's actually two sets of variables, not just the W's, but also the X's, right? Now, this list of expressions up to degree n minus 1, if I fix all the X's, is a linear system that completely determines the W's. But let's say that I also make the X's of variables. In other words, I get to choose where to evaluate my function. Right? Now there's 2x the number of degrees of freedom there were before. There's more flexibility in deriving my integrator. And so I can just keep writing more of these expressions. In fact, I can just write twice the number that I had before. Yeah, so 2n minus 2, 2n, whatever. And what am I going to get? Well, I get a giant system of equations to solve jointly for both the x's and the w's. Isn't that cool? And what I'm going to end up with is a quadrature rule that works perfectly for polynomials of extremely high degree, right? Now, let's think about the drawbacks of a strategy like this. Now, before, we had this very elegant way to compute the w's, right? So if I'm just given the x's, computing the w's is a linear function. But now I have expressions in x's and w's with like very high powers of x's, which are now variables in my problem. So this thing actually falls into the category of problems we've already talked about in this class. This is a nonlinear root finding problem. And so a very typical way to derive a very high order degree accuracy quadrature rule, if you're allowed to move the x's around, is to write a bunch of expressions like this, and then basically you have some really complicated root finding function and some function g of all the w's and all the x's all at once by just writing all the rows of the system down. And your job is to find a point where g is equal to 0. Yeah? And you can solve this thing numerically. For instance, you could use Broyden's method or any of the other things we've talked about before. And what you get is a really accurate quadrature rule. Isn't that clever? This is such a neat idea. Now, it turns out for like up to, I think, I equals 2 or 3, these are known in closed form. If you look on the Wikipedia page for Gauss quadrature, not curvature, that's my other class, you'll find it. And they're really interesting. Like they're odd integrators. Like the x's are not evenly spaced. They're chosen in some particular fashion that essentially accounts for the fact that like polynomials have different curvature in different places. And this is just an interesting way to get some of these rules. And in fact, moreover, it could be that like maybe I happen to know for the problems in my domain that I don't care about polynomials. Like I really care about polynomials and like a few cosines and sines or something like that. For each of those, I could write one of these systems down and then just solve it for our integration rule. Yes?
Oh, no, I just was going to ask if the g is like a 2n, RT2n vector, but you can collapse it.
Can I collapse it? Yeah, absolutely. I mean, you can write the w easily as a function of x. So it's really just a function of the x's. I don't think that matters. This is basically the Shor complement of this problem. Yeah, good question. So anyway, this is a clever way to write integrators down. Essentially, you say like there's like 10 functions whose integrals I know, so I might as well kind of bake those into my integrator. So I write down a rule like this, and now I have this system. If you want really, really hard to think about math problems, one question that you could ask, for example, even just specifically for polynomials, like here, I wrote down an object that if you take an algebra class, is called an algebraic variety. Right? In other words, this is like a weird root finding problem in a high dimension that's polynomial. Is it even obvious that a solution to this problem exists? No, right? Like, so it could be the case that there are like certain Gauss quadrature rules that just aren't out there. Like maybe it's possible that like I just can't come up with a quadrature rule that knows how to integrate e to the x. Like we don't know. And that kind of makes sense because like are integrals this? No, this is this is an approximation, right? And so you're sort of like choosing a form for this expression that happens to work well on some set of functions you've determined ahead of time. But that was a choice, and so for each one of those, you have to justify that you can do it. I think the typical way to justify it is to just derive one of these things, and then a posteriori you say like, oh, well, I found a root, so I'm good. Right? Does everybody understand the idea of Gauss quadrature? Really clever idea. So we've got 5 minutes left. That's not enough time to derive other rules here, but I did want to just briefly mention the tip of another iceberg that you guys should read about, which is called adaptive quadrature. It's exactly what it sounds like. Here's the thing about quadrature rules. Not all samples are created equal. So for instance, let's say that I have a function and it's like close to 0 in low frequency, and then suddenly it's like wiggling like that over here. Would it make sense, if the integral I'm trying to compute is from 0 to there, to evenly distribute samples in this interval? No, right? So in particular, obviously the terms that are here are contributing a lot more to the integral. And moreover, the function is crazier over here. But here's the problem. Do I know that? Like, it's easy to plot it and for us to eyeball it, but of course the computer, what does it do? You put it in an x, it gives you the f of x. It doesn't tell you anything about the shape. And so there's all this set of adaptive quadrature rules which are trying to strategically choose the x's. And there are all kinds of interesting ways that you can do that. So for instance, I think a very typical one is you start out with one of your favorite composite rules. And one thing that you can do is just remove half of your samples, right? Like, so for instance, every other sample I'm just going to get rid of. And I'm going to see how the integral changes locally, right? And if the integral is pretty stable to removing a bunch of samples, then probably I don't need to keep adding more samples in that region. And so one thing you could do is kind of compare, for example, like midpoint plus midpoint versus just this full midpoint here. And if they basically agree, then really I should put my samples in the next iteration of my algorithm somewhere else, right? So that's a very typical heuristic. In fact, there's even more beautiful things you can do. If you're into this, this is like one of these fun areas of math that's like very tangible, and the rules are quite simple, and then like each one of them is the tip of a nasty iceberg. Like Gaussian quadrature makes perfect sense until you realize like, oh god, this is some horrible high-dimensional algebraic variety, and I have no idea if there's even a solution to this system of equations. Similarly here, you can even mix and match these things. So for example, Chronod integration rules are some like fun mishmash of the two things I've written here. So for instance, one thing you could do is evenly space your samples, and then the next time around, do a Gaussian quadrature rule where you say maybe half of my x's are known, and the other half are now allowed to move around, because I already sampled those data points. There's no reason to throw them away, right? And now you'll end up with yet another quadrature rule that falls into these different categories. So anyway, these are the kinds of problems that people study in this domain. I don't think it's worth more than one lecture in this class, but hopefully you guys get the idea here that essentially, here are the high-level points to take away today. Simple quadrature rules are quite counterintuitive in terms of the error rates. That I think they don't kind of step up in terms of error the same way that you might expect from a Taylor series. And the basic kind of intuition why is that they're integrated around some symmetric set of points, and when I do that, your integrals tend to have a bunch of terms that cancel. And in fact, moreover, the lower order terms, the constants in front of them, tend to flip backward, which is totally surprising. Moreover, in fancy versions of quadrature, you don't have to make the x's evenly spaced. Not all data comes on grids. And in fact, sometimes you're even able to just strategically choose your x's, right? So adaptive methods are examples of methods where you kind of collect some data and then find more. And then Gauss quadrature rules are examples where maybe you do want to determine the x's a priori, but you know that there's some class of functions that your data is likely to be in, and you want your integrator to work well. Any questions? I saw one over here, but I forgot who. Nope? Okay. Well, for once, maybe we'll end a minute or two early. Everybody have a delightful holiday. And I will see you on Monday, where we'll talk a bit about high-dimensional integration, where all these rules fall apart and algorithms go to die. And then we'll talk about differentiation.